for today. And today we will, now we have a talk by Professor Takata on life cycle evaluation, and we will talk about modeling and simulation of circular manufacturing using discrete event simulation.
So good afternoon. Regarding the life cycle evaluation, I want to talk about focus on the simulation for evaluating the life cycles. So, as I already told, designing and managing the circular manufacturing is a complex work. So because there are numerous variations in realizing the circular manufacturing in terms of the life cycle options, life cycle business options, and so on. So in addition to the design of the circular manufacturing, there could be many issues in its management. So I'll touch on it, or what kind of the issues we will have. In general, designing and managing the circular manufacturing is complicated compared to the conventional linear manufacturing because of the existence of groups in its items flow. So if you knowledgeable about the control engineering, if you have a feedback loop, then the behavior of the system become quite complicated, or the not so simple, straightforward. So there are so many management issues on circular manufacturing, but I want to focus on the two issues: matching operations between items conditions, because for introducing the reuse option, reuse part has different conditions, usually the linear production manufacturing, usually the condition of the product is controlled strictly, and usually it has the same condition. But in the case of the circular manufacturing, reused product or parts have different conditions depending on the mode of the usage or the user's behavior. So we need to matching operations between items condition and the user requirements. So this matching operation is quite important to efficiently use the reuse the parts or reuse the product. And also there are multiple circulation ways. As I explained already, so there are several kinds of the circulation path. Products reuse, module reuse, part reuse, or material recycling. And also the reuse or reuse could be a open reuse or closed loop reuse, using the product for the same purpose or the repurpose, and so on. So as I already said, that in linear manufacturing, the product are manufactured in order of customers' demand. So this is kind of an ideal situation, but when you have an order, then provide the product. So it's a simple operation. I mean that the products are not different from each other. They are also already same condition. On the other hand, in circular manufacturing, products are returned at user's discretion with different conditions depending on ways of usage. So properly manufactured product should be selected, or remanufactured product or the reconditioned product. The level of the recovery, functional recovery is different, but anyhow, so proper product should be selected to best fit to the customer's requirements. So there are group of the customers with different requirement, and you may have a stock of the return product and with different conditions, then which product matches to the whose requirement. So this kind of the matching operation is necessary to make the reuse operation effectively. So also multiple circulation paths means like in the case of the lithium-ion battery of the car, the primary reuse should be the battery, return battery is used for the car. But if the battery deteriorates and when it does not satisfy the user's needs, then that will be sent to the used for the stationary batteries for the houses with solar panel, for example. So in this case, you need to control in which condition you should send the secondary use. So maybe there is some kind of the conditions or the thresholds to switch from the primary use to secondary use. So therefore, so we need to select life cycle options, and also we need to set a certain kind of the parameters to control the flow of the material, parts and products. And we should look at a certain kind of the KPI and KMI. KPI means key performance indices, and KMI means key management indices. We evaluate these indices to select proper way and proper parameters, management parameters. So like average total value provided by items during its life cycle, average life utilization rate of each item. Life utilization rate means if the product in average 10 years life, but if the user discard it in 5 years, discard the product in 5 years, then life utilization rate is 50%. So this is the way, this is the indices to indicate how the values of the product are actually used or not. So also in the management side, there could be an intermediate stock of items in circulation path. So product returns, and that will be a hold in the warehouse, and then provide to the users. So in the circulation path, there should be some kind of the storage, and how many items are in that storage is one of the indicator for the efficiency of the circular manufacturing. And also the circulation lead time is also the important KPI. And as for the KMI, life cycle cost, environmental load, resource consumption for such as a group of customers in the market during a certain time period. So life cycle cost for the resource efficiency or the environmental efficiency and so on. So they are the top indices for top management indices. So you need to evaluate these indices whether your circular manufacturing system works well or not. So for evaluating these indices, we need an appropriate tool in addition to the conventional LCA. So LCA means, that LCA stands for life cycle assessment, and it looks at the life cycle of the product, but one life cycle of the one product. So if you look at this product, for example, you can evaluate the life cycle by life cycle assessment, how much environmental impact created by the life cycle of this product. So in this way, first you need to identify the life cycle of the product, and then you evaluate, you make an inventory analysis. Inventory analysis means what kind of the material and how much material input to the process, in each process, and how much output. So how much consumed, how much output. Then enumerate every material. Then you can analyze you can make the so-called inventory analysis. And then this kind of the input-output material has the impact to the environment or the ozone layers, ozone depletion, and so on. So different kind of the environmental impact. So you should analysis. And then there could be a different kind of the impact, and you should for the purpose of which one is better, so you need to integrate these different kind of impact. So this is called interpretation or integration of the impact. So then you can say which product or which life cycle is better in terms of the environmental impact and so on. So, but as I told you, this LCA is evaluation method of the one product, one life cycle of one product. But if you look at the manufacturing system, you have a number of the customers in a certain market, and you are providing the many products time to time. So you need to evaluate such as the environmental impact for satisfying the number of users in the market for a certain period of time. So in this kind of the simulation, in this kind of the evaluation should be done by using the so-called life cycle simulation. So if you evaluate this kind of the product and parts and material flows, then you can, with the data of the life cycle assessment and life cycle costing, you can evaluate the total resource consumption, environmental load, and life cycle costs for satisfying a certain group of users during a certain period of time. So the time should be not 1 or 2 years, because usually the products are used for example, in the case of the home appliances, 10 hours, 10 years, or 5 years. So that amount of the period should be looked at to evaluate whether your reuse circulation system works well or not. So in general, there are several kind of the simulation models or simulation methods, which are discrete event model, system dynamics model, and agent-based model. And in life cycle simulation, every kind of the models are used so far. But unfortunately, so there is not so well-established life cycle simulation system which can be commercially utilized. There are so many life cycle simulation systems are developed so far, but mainly for the research purpose. So in our case, we use a discrete event model. So this is the most common way to simulate the life cycle. And discrete event simulation, the typical example of the discrete event simulation is a queuing simulation. So in the simulation, identify the event, and event changes the certain type of status, system status. Then this kind of the change is reflected in the model, and then search is the next event, and event, and in each event some changes. So that is repeated to simulate the certain kind of the activities. So LCS, life cycle simulation, need a kind of characteristics, because we need to look at each individual item, behavior of each individual item. I mean that so you need to look, of course you need to look at the product which are produced, sold and used and returned and so on. But usually the products are disassembled and the part are extracted, and then part may be reused for another product. So that means that it's necessary for us to control each part or each component individually. You need to trace the usage of not only the product but also the components. So that makes this kind of simulation a bit complicated, or the yeah. So, and also the simulation is executed for selecting the proper life cycle options or the life cycle strategies. So you need to model the various life cycle scenarios, and I already did this one. And not only the characteristics of the product, but also we need to represent the characteristics of the users. So the state of the product depends on who uses the product, or how used the product. And depending on the usage process, the function of the product may deteriorate, or the physical condition of the product deteriorate. So that kind of the change should be also evaluated. And you need to control the reuse flow, the items flow, so that can be represented in the simulation also. So as I told you that many LCs has been developed so far, there are few general purpose systems which satisfy all these requirements. So again, that why we need a life cycle simulation, because site matching operation is required. And also there are several ways of the reuse or repurposing and so on. So we have developed a life cycle simulation system using the general purpose manufacturing systems simulation. This is a commercial simulation system, and we modified that simulation system, or the improved simulation system to enable the life cycle simulation. And I want to show you the example of the simulation, lithium-ion battery, EV's lithium-ion battery simulation. So as I already said that the primary use of the lithium-ion battery is for the car, and the secondary use is for the stationary battery. And in this example, we assume that the products are sold to the user without discriminating between newly produced ones and reused ones, as far as they satisfy the user's needs. So, depending on the user's requirement, we can provide the reused parts or reused cars. And we assume the two different kind of the sales modes. First one is unseparated sales mode. That means returned car is cleaned and reconditioned and sold to another user. And the second one is a separated sales mode. That means the returned car, from the returned car, the lithium-ion battery are taken out, and then car body and batteries are stocked independently. And user has different kind of the requirements. One user may want to have a new body, but doesn't care how much, how long the fleet distance is. So they may use the car to drive inside the town, not long distance drive. But another user may use the car for the long distance drive, so 500 kilometers and so on. But he or she doesn't care the appearance of the car, whether the model is old or not. That's they don't care, for example. So in this way, user has a different kind of the requirement, and to satisfy these users, it is better to separate, to store the body and lithium-ion battery separately, and choose the different body and lithium-ion battery, and then assemble it to provide the users. So, for modeling the users, average distance per use. The first one is the number of the years until the user ceases to use the vehicle. So one user drives the car only 3 years and want to have a new car, but another user may use 10 years or 15 years. So, and how long they drive in per year, annual mileage, or the maximum distance per use. So these are the characteristics of the EV users. On the other hand, in stationary battery users, the number of years until the user ceases to use not the vehicle, stationary battery. household electricity consumption, how much electricity they need in their house, and solar generation capacity. And these are the characteristics of the users. And we collected data and distribution of, for example, for annual mileage, there is a data how the mileage is distributed each user by user, and then we create the distribution function and assign the value randomly generated from that distribution patterns. And also we need to model the condition of the lithium-ion batteries, and usually we use it is used to indicate the state of the battery which we call S08 state of health, and that means how much capacity remains compared with the new battery. The SOH indicates the ratio of the current capacity of the leaves to the rated one. So it corresponds to the driving distance, so with which can be drawn without charge. And also we collected the data from the car manufacturer, how the battery deteriorate, and then model this which is included in the lifecycle approximation model. So this is just the rough flow of the lifecycle simulation. So this is the product process, primary use and secondary use, and go to recycle. And sorry, this is unseparated sales mode, and this is for the separated sales mode. Okay, so I don't want to go into the detail of the parameters, but anyhow, this is the amount of the number of the users we assume. So we need to identify the users and the products, each product and each users. So if the number becomes big, so it is quite heavy for simulating. Therefore, we limited the number of the users at 1,000, and this is for the EV users, and 300 for battery stationary battery users. And the simulation period was 35 years, because the average usage period of the car in Japan is about 13 or 14 years. So, and three different conditions, low, medium, and high, and we assigned the threshold for determining whether the ribs and bodies should be reused. So this is just one of the examples of the value provision of each ribs. This is just 10 ribs picked up from the 1,000 ribs, and so the dark blue is a initial stock, and light blue means the first user, second user, third user, and the orange means stationary battery user. So this means depending on the product, so how they are used are quite different from each other. So that means the value provision of each rib is varied depending on the user characteristics. So and this is the average value provision. The average value provision of 10 ribs, which were randomly picked up among ribs that were exhausted and sent to recycling. The lower the reuse conditions, the more the value the ribs can provide, because there are a certain number of users who are satisfied with the lower SOH than the threshold value even in the condition L. L means a lower threshold. The separated sales mode provides more values than the unseparated one because there are more possibilities to provide ribs that fit the user's requirement. So we focus on the most efficient scenario, a separated sales mode with low reuse condition. In this case, the total number of ribs that were exhausted and sent to recycling was about 340, whereas the total number of ribs input to the sales process was about 2,700. Since the number of the users was 1,000, there are large discrepancies between the number of the input items and that of the output items. That means, input or the sold cars, the total number of the sold car becomes 2,700 compared with the users. So of course, the user changes the cars sometimes frequently. So, but considering this kind of the more changes of the car, for the 1,000 users, 2,700 input is a bit big number. So if you look at this process, selective assembly means depending on the user requirement, the provider select the body and the lithium-ion battery. So in this input of this process, if you look at the SOH and the volume stock, input volume, provided volume, then you can see that the lower SOH input and provided value coincide each other, but here there are big volume of the stocked leaves that are not provided to the user. So why this happens means that in this setting, if the user requires more than the fleet distance, that is the SOH, 100% SOH, for example, if with 100% SOH, the car can drive 500 kilometers, but the user requires more than 500 kilometers, then for that user, in this first setting, the new leaves should be provided. So, but when the user says that I need 600 fleet distance, but the maximum fleet distance is 500 if you use even if you use a new battery. So in that case, so the user need to recharge the battery during the drive. So in this case, so 95% SOH and 100% SOH doesn't make big difference for the convenience of the users. So anyhow, so you have to recharge during your drive. So then we changed we changed the rule of the providing the battery to the user. 95%, even though the user who need more than 500 fleet, we can provide more than 95% SOH battery. So then, in that case, okay, so this is before changing the rule. Now after changing the rule, also there's a bit stock amount of the stock, but almost these stocks are disappeared by changing this kind of the rule. So I don't want the detail of the analysis, but what I want to say is that the setting the parameters to control the flow of the material or the product is quite important. So that is true in the case of the manufacturing management, as production management. So how you can coordinate the input material or how you can control the each takt time and so on. So if you want to make the efficient production, you need to control your production system very precisely. And this is also said to this is also true in the case of the circular manufacturing. So management of the flow control is quite important to realize the efficient circulation of the material. So, and to evaluate this kind of the situation, the life cycle simulation is also quite an effective tool. Okay, so for planning and managing the proper life cycles of the items in the circular manufacturing, we need a powerful to evaluate them. For this purpose, we developed a general purpose life cycle simulation system for modeling and evaluating various life cycle scenarios, including multi-tiered circulation. Multi-tiered means the primary use and secondary use and so on. The LCS system can model and trace the behavior of each individual item and user. This enables the system to be used for finding the bottlenecks of the item's flow and improve the efficiency of the circular manufacturing, as I just explained. The LCS system has been applied to the simulation of multi-tiered reuse of lithium-ion battery of the electric vehicles. Leaves are reused for EVs as primary use and then reused for stationary battery as secondary use. We demonstrated the effectiveness of the simulation for improving the managerial rules of circular manufacturing, taking an example of the allocation rule of leaves to the users in terms of SOH. Okay, that's all. Thank you very much for your attention. Any question?
Questions from the audience?
Sir, these LCAs and LCS, we talked about the product perspective. All these LCA and LCS were talked about the product perspective. Is there anything like any assessment analysis we can do in the process? The product maybe can skip some steps, so it can directly energy perspective. Any assessment we can do for that?
You mean that your question is whether the energy or the
like any energy usage or material usage. Again, after the primary usage, the product may again go to the from the start. So in that, instead of going there, I can go to some step.
Yeah, so whether the LCS can evaluate this kind of aspect. Yes. So we modeled each processes, and if you know that how much energy is consumed, for example, in each process, then the life cycle simulation can count how many times this process are activated. Then, if you then from that you can calculate how much energy are consumed in this process during the life cycle or during the simulation time. So in this way, so you can evaluate how much energy you can consume for providing the certain market for the certain period of time. So we can model the period times in the explicit way in the case of the life cycle simulation, but in the LCA, LCA doesn't take the explicit time explicitly. So that's the difference. So the important thing is that not one product, look at the one product, but you have to look at a certain market and certain period of time. So that's a big difference. Is the answer for you? Okay, another one?
Any other questions?
So how much reliable are these simulation results if we compare with the real world result in case of life cycle calculation?
Mm-hmm.
Is there a broad precision or it's very precise?
Pardon?
So if we compare the real life cycle and simulation life cycle results, how reliable the simulation results are?
Yeah, that is a very important point because if we have a many circular manufacturing system in practice, then we can compare the result of the simulation and the actual situation and prove that the simulation is quite precise or not. So, but unfortunately, there are not so many, not quite seldom to have this kind of the circular manufacturing. So we cannot make we cannot prove the correctness of the simulation system. But you know, this is how can I say, to develop a new system. This kind of situation happens always when you develop a new system. So you should simulate by using the data as much as possible. Then, of course, the prediction may be wrong, but although I think it's better making the simulation is it's better to execute the simulation than forget the simulation. Yeah, that is a very important point, and always it was discussed when we proposed this kind of the simulation. So, but the important thing is what kind of the data you can collect and reflect in the simulation model. Thank you very much.
Any other questions? Okay, if not, once again, thank you, Mr. Takata, for the talk.
Thank you very much.
Okay, so now we will start the participants' activity. And so the first thing is that we divide into groups. So if you have found your group, then you can be okay. If not, then we'll allocate the groups to you.